volume cycle, right? So first we will draw PVTS diagram. Let me recall quickly. Then we will go to the problem directly. So as we know, Otto cycle is a constant volume cycle. All petrol engines works on Otto cycle, right? So easy to remember. Just mirror image of PV diagram is the TS diagram. Okay, right. This is 122 isentropic compression, right now. So this is 122, right? 2 to 3 constant volume heat addition. So this is heat addition Q in. 3 to 4 isentropic expansion, then 4 to 1 heat rejection at constant volume Q out, right? So isentropic entropy is constant here, then constant volume heat addition, then isentropic expansion, then constant volume heat rejection, right now. And we came to know the efficiency, air standard efficiency of Otto cycle is equals to 1 minus 1 by R power gamma minus 1, where R is the compression ratio. R is the compression ratio, right? How to define compression ratio? Hello? Right. So where R is the compression ratio, that is the volume at the start of the compression by volume at the end of the compression, or it is also equal to expansion ratio, volume at the end of the expansion by volume at the start of the expansion, right? So right, we'll start problems. Okay, so I'll write the problem. An air standard Otto cycle is operated with the following data. Okay, right. So maximum cycle temperature and pressure is given. Maximum cycle pressure is equals to 5 megapascal maximum cycle temperature is equals to 2250 Kelvin, and minimum cycle pressure and temperature also given. Minimum cycle pressure is equals to 0.1 megapascal and minimum cycle temperature is equals to 300 Kelvin. So what is asking, determine work output. W is asking work output per unit mass, means kilojoules per kg. Kilojoule is the work, per mass is kg is asking, and a thermal efficiency of Otto cycle. Thermal, these two things is asking, right? What is the data given? Only 4 data is given, means so maximum cycle pressure is given, minimum cycle pressure is given, maximum cycle temperature, minimum cycle temperature is given, right? So with this data, we need to calculate the work output as well as the efficiency of the cycle. Okay, right. Now tell me, observe this PV and TS diagram where the pressure is maximum.
P3, sir.
Where we will get the maximum pressure? P3, very good, right? So maximum pressure is given as P3, and where the pressure is minimum?
P1.
Where the pressure is minimum? P1, right? So remember, from this unit you will get either derivation or problem. 99%, right? either derivation or problem or combination also you will get. Okay, right. And maximum cycle temperature as usual, you can see TS diagram. The maximum temperature is at 3, therefore it is T3. Minimum cycle temperature is observed at point 1, and this is T1. Sir, lab lo not sir. Close year e semester है sir. हाँ. చూడలేదు సార్. సరే సార్. Students wait 1 minute. సార్ ఫోన్ కాదు స్విచ్ ఆఫ్, రెండు స్విచ్ ఆఫ్ ఉన్నాయి. ఏ ల్యాబ్లో ఉన్నాడు సార్? గణపతి ఎవరున్నారా ఆయన దగ్గర అసిస్టెంట్? ఇదంతా ఇప్పుడు నేను రికార్డ్ చేస్తున్నా సార్. ఆపలేం, మళ్ళీ అది కట్ కట్ అవుతుంది. గణపతి సార్, సార్ రవి సార్ ఉన్నారా మీతోనే? ఒకసారి ఫోన్ ఇవ్వరా? సార్ వరప్రసాద్ సార్ కంటే వర్క్లోడ్ వేసినారు ఈ సెమిస్టర్? మనోజ్కి వేసినారు కదా? సార్ ఒక్కసారి అంటే హెచ్ఓడికి ఫోన్ చేయండి సార్. నేను క్లాస్లో ఉన్నాను సార్, రాయిస్తుంది. స్విచ్ ఆఫ్ అయింది. గణపతి సార్ దాంట్లో చేయండి, మాట్లాడండి ఒకసారి. ఓకే. Students, sorry for the inconvenience. Okay, right. So P1 is given, T1 is given, P3 is given, T3 is given, right? Now, as we know, the process 2 to 3 is, which is constant during the process 2 to 3? The volume is constant, right? So let us first write 1 to 2 first. 1 to 2 is the isentropic process, isentropic compression, and for 1 to 2 I can say P1 V1 power gamma is equals to P2 V2 power gamma, and I know compression ratio is equals to V1 by V2. That thing, right? And right, so V1 by V2, if I want to write in terms of pressure ratio from equation of state, I can write P1 V1 by T1 is equals to P2 V2 by T2, and from this V1 by V2 is equals to P2 by P1 into T1 by T2. P2 by P1 into T1 by T2. So therefore, for constant volume process, right? For constant constant volume process, V2 equal to V3, that is 2 to 3. Okay, then we can write for 2 to 3, P2 V2 by T2 is equals to P3 V3 by T3, and 2 to 3 volume is constant, can be cancelled. Therefore, I can write P2 by T2 is equals to P3 by T3. I can write right now. So therefore, compression ratio, I have P1 value, I have T1 value, and I have P3 value as well as P3 value. Okay, right. If you substitute, I don't know P2 value, I don't know T2 value, right? So from this, I know P2 by T2 is equals to P3 by T3, right? Here, this P2 by T2 can be replaced with P3 by T3 because I know maximum pressure, maximum temperature, minimum temperature. Therefore, V1 by V2 is equals to T1 by P1 into P2 by T2 is replaced by P3 by T3. Okay, right. So what is V1 by V2? V1 by V2 is nothing but compression ratio. So I know T1 value. T1 should be in Kelvin. Yeah, already it is in Kelvin. T2 should be in Kelvin, and P3 by P1, anyhow it is ratio, whether it is in bar or Pascal, anything can be cancelled, right? So if you substitute, T1 is equals to 300 divided by T3 is equals to 2250 into P3 value, maximum pressure 5 bar divided by minimum pressure 0.1 megapascal. Yeah, simplify and tell me this value. That is compression ratio. All of you open the calculator. So we got R is equals to, simplify and tell me.
Sir, 6.7.
6.7. Okay. Therefore, we got compression ratio equal to 6.7, right? So as we know, the thermal efficiency of Otto cycle can be calculated by using 1 minus 1 by R power gamma minus 1, where R is the compression ratio and gamma is the adiabatic index. As we know, the air standard efficiency is the working fluid is the air. So therefore, efficiency of Otto cycle is equals to 1 minus 1 by R power gamma minus 1, where R is equals to compression ratio and gamma is equals to adiabatic index. So that is the value of adiabatic index for air is equal to 1.4. So gamma value is equals to 1.4. Then take the values and substitute 1 minus 1 by 6.7 whole power 0.4. What is this efficiency?
%50%, sir.
Exactly.
Yes, exactly.
50. 50%.
Yes, sir.
Any other value? Yeah, 0.5. Okay. And as we know, the efficiency is also equals to work done by heat supplied. Work done by heat supply, right? Because I need to calculate work done also. Here I want work done as well as the thermal efficiency. That work done I want to with respect to mass. Okay, right? In order to calculate work done, I know already efficiency. If I am able to calculate the heat supplied, therefore I can calculate work done, right? So first let me calculate heat supplied. In which process we are supplying the heat? Heat is supplied during 2 to 3 process. Agree? 2 to 3, that is constant volume process, right? Therefore, heat supplied per mass, per mass means M is equals to 1. Heat supplied per mass equal to CV into T3 minus T2. CV into T3 minus T2, right? What is CV? Specific heat at constant volume. This value is fixed, you should remember, or sometimes you will give in the problem. The value is 0.718 kilojoules per kg Kelvin. Kilojoules per kg and Kelvin. Okay, this value. Okay, now T3 we know, but T2 I don't know, right? So how to calculate T2 value? For that, you should know the relation between temperature and volume, right? So by using these two equations, that is equation of state and isentropic compression, we already solved so many times. This is one equation, and second equation is P1 V1 power gamma is equals to P2 V2 power gamma. And if you solve these two equations, you will get the relation between, means I want to eliminate the pressure. in this equation with respect to volume, right? So here P1 by P2 I can write. So P1 by P2 is equals to V2 by V1 into T1 by T2. That is one equation, and from this I can write P1 by P2 is equals to V2 by V1 whole power gamma. Then substitute this P1 by P2 value in this equation. Okay, therefore you will get relation between temperature and volume. T2 by T1 is equals to V1 by V2. After substituting all those things, if you simplify, you will get this one. T2 by T1 is equals to V1 by V2 whole power gamma minus 1. What is V1 by V2? V1 by V2 is nothing but the compression ratio. We already have this value. And gamma is equals to 1.4, and T1 is also given. The value of T1 is equals to how much it is? 300 Kelvin. The value of T1 is equals to 300 Kelvin. We have all the data. Therefore, T2 is equals to 300 into R power gamma minus 1, 1.4 minus 1. Can you keep in 6 almara? There on that. Again, I will forget. Okay, now tell me, R value is known. R value we got it as how much? Compression ratio
6.7.
6.7. Yeah, substitute the value and tell me.
Sir, 642 Kelvin, sir.
642 Kelvin. So T2 is equals to 642 Kelvin, and T3 is given as how much? 2250 Kelvin. So therefore heat supplied is equals to CV. It should be in joules. 0.718 is the 0.78 is kilojoules per kg Kelvin. Therefore it will become 718 into 2250 minus 642. How much it will be? The units you will get in terms of joules per kg. Kelvin will be cancelled. Heat supplied per unit mass. How much it will be?
One 1154.5 kilojoules, sir.
Q supply per mass 1155. Joules or kilojoules?
Kilojoules, sir.
Kilojoules per kg. Okay. So therefore, once you know heat supplied, work done is equals to efficiency into heat supplied. So we got efficiency is 50%. That is 0.5 into 1155.
577.3, sir.
577.3 kilojoules per kg. Yeah. This is the work done, and we calculate thermal efficiency. Is it clear?
Yes, sir.
Yes.
Right. We will go to next problem. Let me give a diagram, state diagram as it is. Okay. Right. Now, next problem. In an air standard Otto cycle engine, the temperature at the end of the compression stroke. Temperature at the end of the compression stroke is given. So what is the notation for that? Temperature at the end of the compression stroke. What is compression?
T2,
Which process is compression? Yeah, very good. Temperature at the end of the compression. 1 to 2 is the compression process. So T2 is given. That value is equals to 650 Kelvin given. and the maximum cycle temperature is given. Maximum cycle temperature. This is equals to T3, right?
Yes, sir.
Is equals to 2400 Kelvin. If the engine delivers 700 kilojoules per kg of net work, so W net is equals to given 700 kilojoules per kg, right? And determine the thermal efficiency and the compression ratio of the cycle. Okay, right? So now, so this is the data given, right? So he is asking what is the thermal efficiency and what is the compression ratio. If you know compression ratio, you can calculate the thermal efficiency by using the formula. Okay. Now, can you think how to calculate the compression ratio? We don't have any volume related terms here. Okay, no? But one thing is given, network is given. Right? No? So network is given, and we can also calculate efficiency by dividing the work done with heat supply. Right? One thing, net W net by, so the thermal efficiency can also be calculated. So thermal efficiency is equals to 1 minus 1 by R power gamma minus 1. This is also equals to net work done by heat supply. So in the problem W net is given. If you are able to calculate heat supplied, right? This is equal to thermal efficiency. Therefore, R also we can calculate. How to now? How to calculate heat supplied? Anyone tell me? Heat supplied. Heat supplied. Mass is not given. We can assume unit mass. Heat
Sir,
supply,
CV
tell
into
me.
T3 minus.
Very good. Cv into T3 minus T2, because in process 2 to 3 we are adding the heat. So therefore by addition of the heat, what happens to temperature? Temperature is increased. Therefore T3 minus T2. Cv value just now we see 0.712. It is in kilojoules per kg Kelvin. If you convert into joules, this is equals to 718 into T3 is given 2400. T2 is also given 650. Therefore, you will get heat supplied in terms of joules per kg. Work done is given in terms of kilojoules per kg. Let us take it as 0.718 instead of 718, because the work done units are in kilojoules. Therefore, we will calculate heat supplied also in terms of kilojoules per kg. Tell me value. Heat supplied.
Sir, 1256.5.
1256.5
5,
kilojoules
sir.
per kg, right? Once you know heat supplied and work done, therefore the thermal efficiency is equals to W net is 700 divided by heat supplied is 1256.5. How much it will be?
Sir, 0.6, sir. 60%.
60%. So this is 60%. That is also equals to 0.6. Now, so this 0.6 equal to 1 minus. Tell me,
1
I
by
can
R
equate
power
this
gamma.
one to efficiency. 1 minus 1 by R power gamma minus 1, right? So from this, tell me R value, where gamma is equals to adiabatic index of K, that is
1.4.
1.4. Yeah.
Sir, how we got gamma?
Gamma is fixed for air, that is adiabatic index. Usually, gamma can be calculated by dividing Cp by Cv. Okay, Cp value is 1.002. Cv is 0.718. If you divide this one also, you will get gamma. This is standard value for air.
So 1.4, sir.
1.4 compression ratio. Is it correct? Check it once. I think you'll get some error. Let me write. So 1 minus 0.6 is equals to 1 by r power gamma minus 1. So r power gamma minus 1 is equals to 1 by 0.4. 1 by 0.4. Okay. And what we need to do, how you calculate it? Which implies r power 0.4 is equals to 1 by 0.4. R is equals to 1 by 0.4 whole power 1 by 0.4.
So 9.9, sir.
Sorry?
9.9, sir.
R value is equals to 9.9. Any other answer, please tell me?
8.9, sir. 9.
8.9. Any other? Is this is correct? Is this equation is correct?
Yes, sir.
Okay. What would that mean? This is the procedure, right? If somebody get me 7 point something, 8 point, okay. This is the way to calculate the compression ratio. Okay, right. We'll go to next problem. Clear this one, students?
Yes, sir.
Hello, students, please reply. Right. Right. Next problem. Right. Consider an air standard Otto cycle that has a heat addition. Heat addition is given. That has a heat addition is equals to 2800 kilojoules per kg of compression ratio 8 and pressure and temperature at the beginning of compression. What is the notation? Pressure and temperature at the
P1,
beginning
sir.
of compression, P1 and
P1 and
T1 value.
T1.
P1 is given as 1 bar and T1 is given as 300 Kelvin. This is the data given. Heat addition is given, compression ratio, pressure and temperature at the start of the compression stroke. Okay, calculate the maximum pressure and temperature in the cycle. Maximum pressure, as we know, this is equals to P3, maximum temperature equals to T3. Then thermal efficiency, then mean effective pressure. Okay, these four values are required. Okay, now heat addition is given CV into T3 minus T2. Okay, right. I know T1 value, P1 value, and compression ratio can be written as V1 by V2. Can I write R value?
Yes, sir.
Right. Now, by using the relation between pressure and volume for 1 to 2, P1 V1 power gamma is equals to P2 V2 power gamma, right? And from this, I can say P2 by P1 is equals to V1 by V2 power gamma. As we know, V1 by V2 is 8, and from this P2 is equals to P1 is equals to 1 into 8 power 1.4. So therefore, I will get pressure at the end of the compression. How much it? Tell me, P2 value, 8 power 1.4.
18.4, sir.
18.4 units will be same bar. Once I know P2, I can calculate T2 as I have a relation between T2 by T1 is equals to V1 by V2 whole power gamma minus 1. V1 by V2 whole power gamma minus 1. Therefore, from this T2 is equals to 300 into 8 power 0.4. This value.
Six 89.2, sir.
Right. T2 is known, P2 is known, right? Then P1, T1 we know, P2, T2 we know, right? So can we calculate T3 because heat addition is equals to heat addition is given that is equals to 2800 that is equals to CV into T3 minus T2. So in this CV value is I know 0.718 I know. Okay. So therefore from this T3 I can calculate because T2 is known. T3 is equals to 2800. Heat addition is in kilojoules, therefore it should be in 0.718 divided by 0.718. Okay, and plus T2. T2 value 689.2. How much it will be?
It's 4588.9, sir.
What about others? Only one guy is answering. Remaining are just simply sitting idle. Huh? Please, you should operate the calculator. I said compulsory question. 4588, right? I got T3 value, right? Now 223 is constant volume process, right? So I know P1 value, P2 value. Then P3 also I can calculate. 2 to 3 process, I can say P2 by T2 is equals to P3 by T3 because volume is constant. So from this P3 is equals to P2 into T3 by T2. P2 value I got it as 18.4 into 4588.9 divided by T2. How much we got? T2 is equals to 689.2. This is T2. Now tell me. First, what I am doing, I am finding all the parameters at all each and every state point. I am finding pressure and temperature. If you know pressure and temperature at all the state points, nothing is there. Just substituting the values in the formula.
So
122.5.
122.5.
Very good. 122.5 bar. Right. I got all the values right, and I think T4 is not there. T4 and P4 are required. Right. How to get 4 value for the process you need to consider 3 to 4, right? So we know T3 by T4 is equals to V3 by V4. V3 by V4. I think let me write equation 3 to 4. For 3 to 4, it is P3 V3 by T3 is equals to P4 V4 by T4. Right. So I want to write temperature volume, therefore I need to eliminate pressure. P3 by P4 is equals to V4 by V3 into T3 by T4. And one more equation, isentropic expansion process, P3 V3 power gamma is equals to P4 V4 power gamma. From this P3 by P4 is replaced by V4 by V3 whole power gamma. So substitute this P3 by P4 over here. Therefore, you will get V4 by V3 whole power gamma minus 1 is equals to T3 by T4. Clear this one? Directly I am sending here. It will come to denominator. If I write in the numerator, minus 1. Already gamma is there. Okay. Right. So from this T3 value, I know T4 I want. Right. So T4 by T3 I can written as reciprocal V3 by V4 whole power gamma minus 1. What is V3 by V4? V3 by V4 is the start of expansion by end of expansion. That value is 1 by R power gamma minus 1. R value is given, it is 8. So therefore, T4 is equals to T3, how much we got? T3 value, where it is? Yeah, here. 4588.9. 4588.9 into R value is 8 is given 1 by 8 whole power 1.4 minus 1, that is 0.4. Tell me this one. This is 4588.
One 1997.4.
1997.4 Kelvin. Now we got all the values. Now let me check what is required here. P3 we got. One is required. P3 we calculate. T3 also we calculated. Now we can calculate thermal efficiency. For thermal efficiency, need not to calculate all those things because directly R value is given in the problem. Directly compression ratio is given. Okay. So thermal efficiency is equals to 1 minus 1 by R power gamma minus 1. How much it will be? R is 8. Gamma is 1.4.
60%, sir.
60.
Yes, sir.
Even you can calculate even if let us say compression ratio is not there, how you will calculate thermal efficiency? Thermal efficiency is equals to net work done by heat supplied. How to calculate net work done? Net work done is equals to heat supplied minus heat rejected. Heat is supplied from the process 2 to 3, CV into T3 minus T2 minus heat is rejected during the process 3 to 4, T3 minus T4. Right? So you have all the data. Let calculate complete this one. Calculate W net here. Network is given in the problem, not given, right? So let us say what I am telling. If compression ratio is not there, how to calculate thermal efficiency? For that you need to use this formula W net by work heat supplied. First calculate W net. CV value 0.718 into T3. T3 value is 4588.9 minus T2. T2 value is 689.2. 689.2. This is heat supplied minus 0.718 into 45. Sorry, heat rejected from 4 to 1, right? Heat rejected is 4 to 1 and 4 to 1. This is 4. Where heat will be more T4 minus T1, right? So this is T4 minus T1. T4 minus T1. T4 value is how much? 1997.4. 1997.4 minus T1 value 300 Kelvin. First tell me what is the this value and then tell me this value. Heat supplied first, tell me heat rejected, then tell me. Then finally we will get net work.
So 2799.4.
Heat supplied.
Yes, sir.
Yeah, 2799.4 minus heat rejected.
One two one 8.7, sir.
1218.7. What is the total value?
One 1580.7.
1580.7 kilojoules per kg. W net, right? So therefore thermal efficiency is equals to W net by heat supplied. So W net we got 1580.7 by heat supplied is equals to 2799.4. How much it will be?
60%, sir.
60%. Earlier how much we got with help of compression ratio?
60%.
60%, right? Anyway, we can solve, depends on the given data. Like that, we can cross check also. Got the thing?
Yes, sir.
Okay, right. So with this, we will stop today. Next class, we will solve more problems in diesel cycle and dual cycle. Any doubts?
No, sir.
Till now.